What I want to talk about today is properties of a special class of curves of metrics on surfaces and how they can be applied to study geometric evolution equations on surfaces again. And most of pretty much everything that I'm going to talk about here is joint work with Peter Topping. So let me start at the beginning. So for the whole of the talk, I want to consider M to be a closed and oriented surface. And really the interesting case that we're going to consider is when the genus is greater or equal to 2. Otherwise, what I'm going to talk about is just not as interesting. Then there's three basic ways to evolve a metric on such a surface. The first one is keeping the conformal class fixed, but changing the conformal factor, so conformal change. The second class is, from the point of view of geometry, doing nothing, but just taking your metric and pulling it back by diffeomorphisms. And then there's a third type that I want to talk about here, and that's horizontal curves. And I say there's these three basic types because you can build every curve of metrics out of these three types of evolutions in a quite simple way. So to be more precise, if you're given any curve, say t maps to some g tilde of t, any smooth curve of metrics, in the first step you can of course use conformal changes by the uniformization theorem to write your evolution of metrics as e to the some conformal factor, say v of t times g hat of t, where now g hat is a constant curvature metric. So here I want to talk about metrics g hat in the space of curvature -1 metrics. So I'm talking about Gauss curvature equal to -1. So we have a hyperbolic metric times a conformal factor. And now you can further split up every curve of hyperbolic metrics in terms of these two other types. So I can write g hat of t by pulling back with diffeomorphisms of an even simpler type of curves, g of t, where now g of t is a horizontal curve. And horizontal means it moves orthogonally to these other two types of changes. So i.e. with a horizontal curve, I mean a smooth curve in the space of hyperbolic metrics such that the velocity is in what I denote as horizontal space. And this horizontal space is so that if I take the Lie derivatives and I add h to it, then this is L2 orthogonal. Together, I'm going to get the tangent space to the hyperbolic guys. And now I can furthermore add in the conformal changes. And now this is in general not orthogonal, but even if I take the brackets like this sum is still going to be orthogonal. So the horizontal space is orthogonal to changes by pullback with diffeomorphisms and by conformal changes. And there's several ways of characterizing this horizontal space. So you can either think of it just using this decomposition as the tensors such that the divergence is 0, and so also that the trace is 0. And on the other hand, a very useful characterization for what I'm going to talk about is to think of this space of real tensors as the real part of a space of complex tensors that we've already seen at this conference, namely as the space of holomorphic quadratic differentials. So I'm going to denote that by, say, curly h of g. In some sense, as the name holomorphic already alludes to, these are really nice tensors. And in some sense, this space H contains only really nice tensors. It's also a finite dimensional space. That very much depends on what G is. And in some sense, this property translates, as we're going to see, to horizontal curves. And horizontal curves will be really nice even if they degenerate. That sounds like a bit of a contradiction, but I hope I can convince you that this is actually a real mathematical nice property. Okay, now why do we care about horizontal curves? So first of all, they're certainly in some sense interesting to study just from this intrinsic point of view. On the other hand, they can be very useful in applications to geometric flows. So let me just say a few words on this already now. I'm going to come back to this later on. So there's different ways in which you can apply these horizontal curves in the study of geometric flows. One way is if you're given some kind of PDE that evolves the metric on a domain, so on the surface, you can try to split up solutions of your PDEs into these three different types, and you can hope by splitting it up in this way, you can actually attack the different components that you get with very different methods. And that's one application that I've done together with Reto Puzzano in the study of Ricci harmonic map flow. So if you consider Ricci flow on surfaces, then this whole splitting up is not necessary because Ricci flow is simply a conformal flow. Now, Ricci harmonic map flow is a flow that you obtain by coupling Ricci flow on a surface together with a harmonic map heat flow that goes from this surface with the evolving metric into a fixed target manifold. And in this way, so the way you couple it, I don't want to go into details, but the evolution equation of the metric will have all three different types of evolution. So it will have conformal changes, pullback by diffeomorphisms, and it will have horizontal curves. And so using this idea, you can actually split up these solutions of this flow, and you can show that the horizontal curve is very well controlled if something like the energy density is controlled. And as such, what you get back is something which is roughly a conformal flow again, now on a background which is evolving, but evolving in a nice way. And we use this for this flow, this Ricci harmonic map flow, in order to establish long-time existence of smooth solutions under certain conditions. Now, the application here I want to talk about most, and really, in some sense, the application that was the inspiration to even study these horizontal curves, is the study of Teichmüller harmonic map flow. So, what is this? So as said, this is a joint work with Peter Topping. So this is a flow we introduced as follows. So we're given some target n. So this is just some closed Riemannian manifold of, so n-gn, but I'm always kind of forgetting the gn, closed Riemannian manifold of any dimension. And then what we wanted to ask is, how can I take a map into this target and deform it in a way that is going to end up giving me a minimal surface, or more generally giving me a possibly branched minimal immersion. And the idea of this is to define this flow, so let me call it THF, to define this Teichmüller harmonic map flow as an L2 gradient flow, not of the area functional, but of an energy. So we consider the Dirichlet energy, which we've seen in a previous talk. But in contrast to before, we do not consider this just as a function of the map, but we consider it as a function of the map and the metric component. So if you do so, where U is now a map from the surface to the target and G is a metric, then if you have a critical point UG of this energy, what U is going to be is not just a harmonic map, but in addition it's going to be conformal. So the critical point, or weakly conformal at least. So the critical points of this energy are exactly minimal immersions, which might have branch points or just constants. So this flow is therefore really designed to find, in a sense, possibly branched minimal immersion. Now, what does this have to do with horizontal curves? If you want to write down the gradient flow of the energy, so how can we define this? What we do is we evolve the map component by the gradient of the energy with respect to the map. But on the other hand, we do not have to evolve the metric component with the full gradient. But what we evolve is just taking the metric component with the gradient of the energy with respect to g, but projected down horizontally. So this is the L2 orthogonal projection onto the horizontal component. And the idea is really the splitting behind there. So you would have, in general, you would need to move in conformal direction. But the energy here doesn't care about conformal direction. It's a conformal invariant. And in general, you would need to move in direction of diffeomorphisms. But you can push all of these diffeomorphisms over to this component. And therefore, it's enough to actually just evolve the metric component by a horizontal curve. The way you can write down this equation, so we've already seen for the energy, the Hopf differential plays an important role. And so in this context, the evolution equation turns out to be 1/4 the real part of projecting the Hopf differential down onto the space of holomorphic quadratic differentials. Whereas this gradient of the energy is just the tension, again, that we've seen before. Now, having this evolution equation, now, what kind of questions do you have to ask? Or what's, in some sense, what's the advantage of G being a horizontal curve? So, on the one hand, this implies, on the positive side, that this projection regularizes the metric component enormously. So if you were to leave away the projection, you would have something which is a lot less regular. And we're going to see in particular that weak information on the thing you project down, in this case the Hopf differential, can give strong information on the velocity of the metric. So that's an advantage. Now, what you might think of a disadvantage, at least at first glance, it forces you to consider several questions, which don't so much have to do with really this evolution equation, but more generally with properties of horizontal curves. So one of the things you need to consider is the properties of the projection And in fact, this is something which is related with the existence of the flow. Another thing you want to consider is what does it mean if the projection of a quadratic differential is nearly zero? Does that actually mean that also the differential is nearly zero, or under what condition does this imply something like that? So you want to understand the relation between quadratic differentials and their horizontal part. And in fact, this is related to the asymptotics. And then finally, you really want to understand convergence properties, regularity properties of these horizontal curves at a pretty precise level. So you want to understand, in some sense, the fine convergence properties of horizontal curves. And this is related to singularities, study of singularities of the flow. Now, in some sense, at first glance, it looks to be, in some sense, a disadvantage to have to do all of these things. But in fact, I would think of this as a very positive thing, because in some sense, it's very nice how the application leads you to a lot of interesting questions just for this general topic of studying horizontal curves. And in some sense, all of the properties you want to prove for the flow, at all times, the proofs of these properties is done by proving some general statement of horizontal curves, and then proving some kind of thing which has to do with studying maps, studying harmonic map flow, and so on, and putting them together nicely in order to get what you would like. So today I want to talk mainly about the third point that I mentioned down there, the fine convergence properties of these horizontal curves. But I want to make some remarks also on the other 2 points if I have time. So let me start by making a quick remark about the first point to get an idea of what kind of properties you can expect of horizontal curves if everything is nice. And everything being nice in this case means that the injectivity radius doesn't go to 0. So let me start with a proposition, which is kind of an old proposition already from, I guess, 2012, and which tells you that this projection has some nice properties. So the projection pH onto this horizontal space, this can be seen as a Lipschitz map, locally Lipschitz. When you look on the right target, on the right domain, and the right domain is on the Banach manifold, M minus 1S, which is the set of all hyperbolic metrics with coefficients in the Sobolev space HS, and say this for S greater than 3. So it can be seen in this way, and what this really means, you can estimate differences of projection in terms of differences of the metrics, really as tensors if you want, times the norm of the K. And the important point is that while here you would expect you have to measure differences in the same space, so the HS space, you need very weak information on the tensor K. So this is really this regularizing effect that I mentioned. What you need is you take L1 and you take L1 and you bound whatever HS norm that you want. Yes? Mainly for, so the thing is, you can do it also on genus 1. There was a flow before.
No, I mean, so you would just start with genus.
Yeah, but you don't have to. So basically, you know that the energy is conformally invariant. So you start in some sense with a, yeah. We start with a nice representative, yeah. And we stay in that class. Yeah, so the type of estimates you get is you can bound norms that, any norm that you want in terms of L1 norm of what you project down. And this gives you strong information, so you get strong regularity on G for as long as. And this is really, the injectivity radius doesn't go to 0 of the surface. And as a result, what you can say roughly is that Teichmüller harmonic map flow behaves as nice as harmonic map flow. Again, as long as injectivity radius doesn't go to 0. And harmonic map flow on surfaces is extremely well understood. You understand in particular that while there might be singularities, at such a singularity all you're losing are so-called bubbles. So bubbles in this context can be seen as maps omega which are from R2 into the target and which are harmonic. So because R2 is nothing else than S2 without a point, you can also think of those guys as maps from S2 to N which are harmonic. And in this one instance, being harmonic implies directly that the maps are conformal, and therefore what you're going to lose at such singular times are just minimal immersions themselves. So if the injectivity radius never goes to 0, you can flow all the way to infinity if you want, and on the way all you lose are the limiting object that you're actually trying to find. So that's okay. Now unfortunately, injectivity radius not going to 0 it's really not clear why this should be the case, and we cannot prove it in general. So I want to make a remark that joint work, so I said this is with Topping from, I guess, 2014, is that if we know that the sectional curvature of n is less than or equal to 0, then injectivity radius doesn't go to 0 in finite time. And in the general situation, it is unclear. So we don't even have a conjecture, we don't have a counterexample, but we don't have a proof of it not happening either. Now, why is even this possibility there of injectivity radius going to 0? So this would not happen if you considered the flow on a torus. Because a big difference between the torus and higher genus surfaces is that on the torus, the Teichmüller space with Weil-Petersen, which is basically just L2 metric, is complete, whereas on higher genus surfaces, Teichmüller space is not complete. So because of this, we kind of put this as a warning, horizontal curves of finite length can really degenerate. And this degeneration, always the only thing which can go wrong in a sense, as said, is injectivity radius going to 0. So what's the picture of this? Let me just draw a genus 2 surface, because any other genus doesn't look nice when I draw it. So you start with a genus 2 surface. Now, the injectivity radius in hyperbolic surfaces going to 0 can only happen in a very kind of well-described way. What happens must be that one of the closed geodesics must pinch, or maybe more of them must pinch, and at the same time this forces the surrounding so-called color to stretch out. So let me maybe draw this with the geodesic homotopic to that guy pinching. So what happens is maybe this part here looks pretty much the same, but this thing here has gotten to be very, very long and very, very thin. And in the end, when you pass to the limit, what you get is a genus 1 surface with 2 hyperbolic punctures looking, getting a bit closer together like that. So the type of convergence you have is described by a geometric version of the Deligne-Mumford compactness, which tells you that if you have a sequence, MGI are hyperbolic surfaces, and the injectivity radius goes to 0, then after passing to a subsequence, and after pulling back by diffeomorphisms, what you get is you have convergence of Fi, say, star Gi, converging locally, smoothly to a limiting guy, G infinity, C infinity log. So you pull back from this surface, except for the collapsing geodesic down there. Now this might sound like all you would ever need for convergence of some objects, because it's smooth local convergence. If you consider flows, however, this is not enough. And there are several things here which are not what you want, so this is not sufficient in applications. So first of all, if you don't have a sequence of metrics, but if you have an evolution equation, if you have a curve of metrics, you expect better than having to pass to a subsequence. That's something you do not want to do. So for horizontal curves, where I always consider horizontal curves of finite length, now what you expect is, first of all, convergence. So for all t going to t, and without having to pull back by diffeomorphisms. Now the first thing seems reasonable. The second thing might seem completely unnecessary, because you might think we move orthogonally to the direction of diffeomorphisms, so why should diffeomorphisms pose a problem? However, in higher genus surfaces, this distribution of assigning to each point this kind of horizontal space is not an integrable distribution. So you can go in horizontal direction and end up on top of the same point in Teichmüller space, but having pulled back with a diffeomorphism. So that can really happen. So maybe another question, why should we even care about diffeomorphisms? I mean, it's the same geometric object. The reason you care about it, in particular in a situation as for the flow up there, is that you couple an evolution equation together with another evolution equation. So if I had to pull things back by diffeomorphisms, then up there, in some sense, also my map component would feel this, and I could not expect the same nice behavior for the map component where that I would get if I didn't have to pull back. So in some sense, this expectation has to do with the goal of the flow, that at the finite time singularity, what you expect is a canonical limit. Or really what you would hope is that you can get a canonical continuation and you want to obtain this not by a surgery procedure, because you really want it canonical. You don't want it to depend on any kind of choices you make, but you want to get it by flowing all the way to t and getting a well-defined limit. So this is really, you need convergence for that. You can't have just subconvergence for something like that. So this is one of the things you would like. Now, getting this convergence, so what kind of convergence you would expect? So certainly you would expect, in some sense, C infinity log convergence. And because you don't pull back by diffeomorphisms, the type of things we're talking about here is getting convergence of tensors. So you would want to know that g of t minus g infinity goes in ck of omega to 0 for all omega, say in the picture up there, in sigma, compactly supported, in some sense in this puncture guy, or maybe in a subset M without, we call this the pinching set. So somewhere where the injectivity radius really goes to 0, something that you lose in the end. Away from that, you would expect nice convergence. Now, I'm still not happy with just having this. So in some sense, when you do this, then what you would expect is on this part, you would have a nice limit to pass to. You would see pretty much all of the information that you had before in this limit, except possibly by things like bubbles that you might lose. On the other hand, there's still a quite large part of the surface that in this picture you would not see. So you would expect here, say on the thick part, you have a fixed omega, a fixed compact surface, compact subset, but then when you actually go to the limit, this part here becomes longer and longer. And on this part, a lot of stuff can happen that you're never going to see in the limit. So if you think of having a map which is defined on this domain, then you will not see what's happening on the degenerating part anymore in the limit. And so a lot of things could be lost and you could not understand what these things are. And in some sense, that would tell you, well, you can continue the flow, but you might lose a lot And the flows that you get after continuation might not have a whole lot to do with the flows that you had before. And that's not a nice property to have. So the second property you would like to have of a kind of really good convergence result is that you would like to know where you have converged, say by a time t naught, the metric has, on the one hand, the metric has settled down, mostly at least, to its limit, as opposed to rather than where the metric still has to do an infinite amount of stretching. So in the application of the flow, this bit, we're going to see it in the limit, and thus in the continuation. And this part is lost. So the hope is that all you lose again are actually the limiting objects you're trying to flow to. So the hope would be there are minimal immersions and nothing else. So that would in some sense be the end goal. Now what can we do? So let me maybe first, that would be interesting, erase this here. Yes? Mm-hmm.
You said that none of this happens if the curvature of the target is negative?
Yes. Yeah. Then it happens at infinite time. But the target is compact, yeah. Yeah. I mean, it's not compact of the target, compactness of the target. You could replace it by having some kind of a condition that prevents you from running off to infinity as well. Yeah. Okay, so the result we can prove in this context is the following. So this is from this year. So let's take G be any horizontal curve on M, say defined on an interval 0t, such that the injectivity radius of M G of t goes to 0 as t goes to t. And additionally, we want this thing to be of finite length. So introducing some notation I need later, we want the L to be less than infinity, where I denote by L of t the length of the curve still has to flow until the final time t. So L2 lengths here. So in this setting, then, what we get is, first of all, this convergence that I mentioned roughly in property 1. So there exists, first of all, a set, a closed set, call it pinching set, F with K between 1 and 3 times genus minus 1 connected components. There exists additionally a complete hyperbolic metric on the complement of F. So call this G bar on the complement, such that G of t converges to G bar smoothly locally on M without F. So without pulling back by diffeomorphisms. That's the first part. Now what is this set and where do we converge? Moreover, there exists a number, say K bar, which depends only on the genus of the surface, such that I can characterize this pinching set by a property of the injectivity radius. So F is given as the intersection for all t less than t of the k bar times L of t squared thin part of m g of t. And these sets, so you already have injectivity radius less than this quantity, these sets are nested. So these will be, in some sense, sub-cylinders of these very long collars that you have up there. And you can describe them very well because these type of collars here can be described explicitly by the so-called collar lemma. So you know how these things look like, and you know that their intersection is going to give you the only region where the injectivity radius goes to 0. So that's one property. And the other property of making kind of an assumption of where do we converge, it's basically outside of this set you have nice convergence. So and for any T naught delta such that the length of T naught times K bar squared is less than delta, we have the following. So we can bound the derivative of dtg in ck in terms of just the L2 norm ck with some additional factors. So yeah, I'll draw another picture later. So what we get is we can bound the ck norm on the delta thick part, either of the surface at time t if we want, or just as well at any time g of s, and measure it with respect to any of the metrics g of s, as long as s and t are greater or equal to t naught. And we can bound this by a constant times delta to the minus 1/2 times, the L2 norm of mg of t. Now this last estimate looks maybe a bit complicated, but really in some sense, the main application of this is the following corollary. So if we have that delta of t goes to 0 slower than length squared, then in some sense the metric will have settled down until time t on the delta of t thick part of the surface. So you can estimate g of t minus the limit ck over the domain delta of t thick. And this goes to 0 as t goes to t. So you get larger and larger regions. You can really tell on which regions you have settled down. Now the essential tool of the proof of this theorem, one of the essential tools, is that along horizontal curves you can pretty well describe how the injectivity radius evolves. And also the origin of this constant here comes from an estimate on the evolution of the injectivity radius in terms of the L2 velocity. Now, I said that this is motivated in some sense by applications to geometric flows. So rather than give more information on the proof of this result, let me tell you what this means now in the application of Teichmüller harmonic map flow. So let us assume UG be a solution of the flow such that the injectivity radius of m g of t goes to 0 as t approaches a finite t. Then what can we say? So first of all, what this tells us is that we should split up our domain. We split it up in the part where the metric has settled and on this part you can apply standard methods from more or less standard methods from harmonic map flow and adapt them nicely in order to prove what we get is that g of t converges to a limiting guy, g bar, up to bubbling. And these bubbles, they account for all the lost information. So all we lose are minimal immersions at this point. Now, on the other hand, you want to split it up in a part where the metric is collapsed a lot. And with a lot, I mean enough, such that the tension of the map in L2 goes to 0, even though the tension can actually blow up. So I have to specify what I mean here, because, I mean, just like that, it's of course wrong. So if you have a finite time singularity, your tension will in general blow up. That's what's causing it. So you can take, the best you can take in general is getting a sequence of times where this tension is blowing up no faster than time remaining 1 over the square root of the time remaining. So that's what you can get. Now, if you're on a thin part, so we talk here really about these very, very long hyperbolic cylinders. These colors, so here you can imagine having, in some sense, this bit attached, and we're talking in some sense about this middle part. These colors, they are isometric to a cylinder, which is very long, equipped with a metric of the form rho squared ds squared plus d theta squared, where this conformal factor in the middle of the cylinder is going to be extremely small. And having smallness of a conformal factor is helping you when you compute tension. So what you can do is you can describe a region in the very center of the color and choose it so that even though this blows up, when I compute it with respect to the hyperbolic metric, if I compute it with respect to the flat metric, it still goes to 0. And this part here corresponds to the T minus Tn to the 1/2 thin part. Or at least a little bit more, O of thin. So basically it's this factor that you need to have to cancel that out. So on this part of the surface, tension goes to 0, and what that means is U looks harmonic in some sense, in this particular sense. And the map looking harmonic is something which you can analyze in detail, and harmonic maps that look harmonic on very, very long cylinders, what you can show is you can say that U of t converges to something which we call a bubble branch. This is something which consists of bubbles, and it consists of mapping close to curves, in some sense curves. So basically, if you have a long cylinder, you might have little points where you have the usual bubbles, so you blow up, you see a minimal immersion. You might have some cylinders. Here, when you blow up, you're going to get an omega, which is from a very, very long cylinder, to n, which is also a harmonic map. But the cylinder is basically a sphere again. So cylinder is a sphere without 2 points. So you get more bubbles. And then you might have regions here where there's basically very little energy, or very little energy per unit cylinder. And on this part, you're going to be mapping close to curves. So these curves connect these different bubbles together. And on this region, that's all you're going to get. So in some sense, this splitting up means we have 2 parts. We have here, in this first part, what we get is a limit plus branched minimal immersions. And on this part here, space. So on this part here, you get bubbles, and they're connected, so bubble branches, I should say. So again, it's just branched minimal immersions in terms of 2-dimensional objects, and there's some curves in there that are connecting them. Now, the convergence to these curves, this is really something which is still quite unclear how that is supposed to look like. So these are 2 regions of the domain. And now the question is, of course, on these 2 regions, everything is nice. So is this all? And that's precisely what the theorem over here tells us. There's nothing else in the domain. So we have this very collapsed part here in the middle. We have t minus t to the 1/2 thin. And on the other hand, we have a part where we can control everything, and that's delta of t thick. And in our case, delta of t, because it goes with length squared, what we can get this control all the way to a pretty much overlap here. So this part here, the collapsing, will be delta of t equals t minus t thick. So we actually have that's the wrong one, sorry. This part here. So this part is t minus t thick. So we actually have an overlap that makes up the whole domain. Yes?
This thing that you call curves or whatever, are you allowing for a cylinder related by curves to get mapped to a segment?
Sorry,
Are you allowing for a cylinder related by curves to be mapped to a segment?
yeah, so these bits here, so the bits where there's little energy, they map close to curve, but we do not know much. They're basically the oscillation on around these circles is going to get exponentially small when you move in, but the curves might do all types of stuff. We have no idea how they look like. Okay, so let me maybe just finish by saying what, in some sense, what this result that I only sketched here allows us to finally prove. So in total, this is together with previous work that we've done before. So this is joint work mostly with just Peter Topping. Some joint work is also with Tobias Huxoll from Warwick and Peter on the asymptotics of the flow, and also with Miao Miao Zhu. So what we can say in total is that Teichmüller harmonic map flow decomposes every initial map from a closed surface to a closed target into branched minimal immersions. That are in general defined on a union of surfaces. Again, they're closed surfaces which have total genus no more than what you started with. And when I say it decomposes it, what you can do, you can get your limiting object, you get your limiting surfaces, say mi, you get limiting minimal immersions, you take your surfaces, you cut out, for example, you have maybe one torus and you have some spheres. Then you can reconstruct your initial map by cutting out little disks here and inserting some cylinders. Maybe you need to add in some more cylinders here, which might form something like that. And by doing so and taking the right curves, what you're going to get is something. The corresponding u infinity is going to be homotopic to the map that you started out with, maybe in this case, which was a map u0 that is defined from your genus 2 guy back. So you can capture all the information you had initially back into minimal surfaces and just curves. And with this, I thank you for your attention.